Hi, in this video tutorial, we'll work through problem 67 from Chapter 18. Chapter 18 covers magnetic fields. This problem focuses on magnetic fields due to current carrying wires. The problem states that the separation distance between two wires in a home power cord is 3 millimeters and that the maximum current in each wire is 15 amps. It also states that the currents run in opposite directions and that both of the currents change directions 60 times per second. Part A asks us to calculate the maximum magnitude of the alternating magnetic field 50 centimeters away from the center of one of these cords, which we'll later find to be 3.6 times 10 to the negative 8 Tesla. When we work through Part B, we'll explain that when twisted together, the magnetic field contributions of each wire nearly cancel each other out to minimize the magnetic field. Now that we read through the problem, why don't we discuss what equations from the chapter are necessary for solving it? From the Biot-Savart law of a short, thin length of wire, we were able to derive the following equation for the magnetic field of a straight current-carrying wire. This equation can be approximated to mu naught over 4 pi times 2I divided by r if the perpendicular distance r away from the center of the wire is much less than the length of the wire L. R is much less than L. We can use this approximation. And this is the equation that we're going to use for part A. Okay, so we know that B equals mu naught over 4 pi times 2I divided by r. So let's draw this out. This is going to be wire 1. And let's just say that the current is coming out of the page there. This is going to be wire 2, and let's say that it's going into the page. There's a separation distance S. Between the two wires. This is the observation location. And there's a distance D from the center of the two wires to the observation location. Knowing this, we know that R1 is going to equal S divided by 2 plus D. R1 is the distance from the center of wire 1 to the observation location. So R1 equals half of this distance, which is going to be from the middle of wire 1 to the middle of both of the wires. So from here to here is S divided by 2. So S divided by 2 plus D is equal to R1. And R2 equals D minus S divided by 2. Because from here to here is also S divided by 2. And we want R2 to represent the distance from the middle of wire 2 to the observation location. Since we were given the maximum value of the current for each wire, we know that for each wire the maximum magnetic field is mu naught over 4 pi times 2 I max over. In order to find the maximum magnitude of the magnetic field at the observation location, we need to find the net maximum magnetic field at that location, meaning B net equals the maximum value of B2 minus the maximum value of B1. Since we were given the maximum value for both wires, we know that I1 max equals I2 max, and I'm just going to call that I. Plugging everything that we know so far into our equation for B net, we can start to solve. So B net equals mu naught over 4 pi times 2I divided by R2 minus mu naught divided by 4 pi times 2I divided by R1, which equals mu naught over 4 pi times 2I, all multiplied by 1 divided by R2 minus 1 divided by R1. This equals mu naught 2I divided by 4 pi times 1 divided by d minus s divided by 2 minus 1 divided by d plus s divided by 2. So let's solve for the inside of the parentheses. D plus s divided by 2 minus d minus s divided by 2 divided by so that's over d squared minus s squared divided by 4. So that all cancels out. And then we're left with s over d squared minus s squared divided by 4. So B net equals mu naught 2I divided by 4 pi times s divided by d squared minus s squared divided by 4. We know that s, since it's equal to 3 times e to the negative 3 meters, and d is equal to 5.5 meters. We know that d is quite larger than s. So if we wanted to, we could approximate and say that that is negligible and that it basically equals 0. So then if we approximated, it would be mu naught over 4 pi times 2I s divided by d squared. But I'm going to use this approximation. 2 mu naught over 4 pi equals 2e to the negative 7 because of the fact that mu naught over 4 pi equals 1e to the negative 7 Tesla times meters per amp. So multiplying it by 2 would be 2e to the negative 7 TMA. So B net equals 2e to the negative 7 I s divided by d squared, which equals 2e to the negative 7 15 3e to the negative 3 divided by 0.5 squared. 3.6 e to the negative 8 Tesla. So moving on to part B, we know that the red wire and the blue wire have currents that are in opposite directions. That means that their B fields are in opposite directions. For instance, using right-hand rule, we know that for the red wire, the B field is going to be out of the page, and that for the blue wire, the B field is going to be into the page. Since we know the directions of the B fields, let's look at the magnitudes. If we look at this as the observation location, we can see that the two B fields will cancel out due to the wires at this location. They will also cancel out due to the wires at this location because of the fact that there's an equal magnitude going in the opposite direction due to this location. So these two B fields will cancel out because they're equal magnitude but opposite directions. The same thing goes for the B fields here and then as far along the wires as the length will take it. Because of this, the contribution of the B fields from each wire will cancel each other out at the observation location if the wires are twisted. Therefore, the net B field at the observation location due to the two twisted wires is going to be at its minimum. In conclusion, Biot-Savart's laws are very important and can be used in many real-world applications.